Hello, all. You might have all heard a story about a man who goes to bath, enters a bathtub full of water, and suddenly finds that some of the water spills out. And he shouts, Eureka! Eureka! He has no clothes. And he runs on the street shouting, Eureka! Eureka! Which means, I have found it! I have found it! I have discovered it! Who was that man? He was Archimedes. And he had discovered an important principle about buoyancy, about the floating of objects. What had he discovered? A very simple fact. When an object is immersed into a liquid, it occupies the space inside the liquid. And to occupy a space inside the liquid, it has to displace the liquid aside. When the man entered bathtub, he occupied some space in bathtub. And because of the insufficient space in the bathtub, the water that was displaced by his body spilled over. He discovered an important fact that object occupies space. Now you might well wonder what's important about this discovery that object occupies space. We all know an object requires space. It occupies space. What's important? It was not only this that he discovered more about it, something more profound about this phenomenon. He then arrived at an important law, an important principle, which is known after his name, Archimedes' principle. Archimedes' principle helps us understand which object will float and which will not. It is the Archimedes' principle upon which the floating of huge ship is based. We know that a single speck of sand, single particle of sand will not float on water. However hard you try to make the a single particle of sand to float on water, it will not. But the huge ship made up of iron and concrete, it does it does float on water. It floats on oceans. The secret was revealed by Archimedes in his famous Archimedes principle. Today's topic is the Archimedes principle. Archimedes is one of the great mathematicians. He was a Greek mathematician. Once a king noticed that the amount of gold that he had provided for the making of crown uh, is not completely used in the crown. Means the amount of gold used in the crown is less than the amount of gold he has provided to maker. He suspected, but he has no proof. He called Archimedes and he asked him to find out about this. Archimedes took a crown, and after he had understood that an object occupies space inside the liquid equal to its volume, what he did, he took a crown and put it into the water and found out and measured the rise in the water level for a crown placed in a water. He then took the equal amount of water in the second identical vessel and then put an amount of gold into that water. The amount of gold equal to the amount that was provided by king to the maker. He found the difference in the level of water rise. From the difference in the water rise level, Archimedes understood that the amount of gold that was provided by king has not been completely used. Some is stolen. And he discovered that some amount of gold have been stolen by the maker. In the diagram you see huge ship made up of iron and concrete carrying huge amount of load in it. They can float on ocean surface. But a single particle of sand will not float, as I have already mentioned. To understand this phenomena, we do a simple experiment. In this diagram, we see a weight, and the weight is measured by this instrument. We see that the weight is around 7 units. When this object is immersed inside water, the weight of this object as measured by this instrument decreases. It was 7, now it is only 4. This means what is the weight of object? The weight of object is basically the downward pull of gravity. W equal to mass time acceleration due to gravity. This is the weight of an object, which is simply the downward pull of gravity. And it is the downward pull of gravity that this instrument measures. But the numbers on this dial are so written that they will directly give us the mass of an object rather than the weight. Upon immersing this object inside water, we see that the weight reduces from 7 unit to 4 unit. So weight decreases by 3 unit. Weight decreases by 3 unit means what? The downward pull of the gravity, that is, it is not a downward pull of gravity. Downward pull of gravity remains same, equal to mg. But there must be some upward force which partially balances or partially cancels the downward pull of gravity. So downward pull of gravity is 7 unit because its weight is 7 when it is in air, but when it is inside the water, the downward pull that this instrument measure is only 4 unit, means there is a decrease of 3 unit. The decrease of 3 unit is due to an upward force of 3 unit acting upon an object when it is inside the water. The upward force of 3 unit from water on this object reduces 3 unit of the total downward pull due to gravity. Total downward pull is 7 unit. So out of 7 unit, this upward force of 3 unit will cancel 3 unit part of the downward pull of gravity, and the total downward pull on this object will be only 4 unit, which is measured by this instrument. So what we understand from this simple experiment is the first thing, that when an object is immersed inside a liquid exerts upward force upon that object, and because of that upward force, a partial cancellation of downward pull of gravity takes place, and the object then have less weight. Now, the amount of upward force which is exerted by a liquid upon an object, it is called buoyant force. And this buoyant force depends upon what volume of an object is inside the liquid. Greater the volume of an object inside the liquid, greater will be the buoyant force. When an object is completely inside the liquid, the total buoyant force acting upon an object correspond to the total volume of an object inside the liquid. Experimentally, it is found that when an object is immersed inside the liquid, of course, some of the water will spill outside when the water is filled up to the rim. Some water spill outside. The volume of water that is spilled outside will be equal to the volume of a part of an object that is inside the liquid. In the present case, we have shown the object completely inside the water. So, volume of the water that spills outside, that volume of water will be equal to the volume of an object. And we also measure that the upward force is 3 unit. And it is found that the upward force of 3 unit is exactly equal to the amount of water that spills outside. And the amount of water that spills outside is actually the amount of water that have been displaced by this object to make space for itself inside the water. To make space for itself inside the water, it has to displace aside the equal volume of water, and that is what we get in this bowl when the water spills outside. So it is found that the upward buoyant force acting upon an object is equal to the weight of the water that spills outside. In other words, it is equal to the weight of water that is displaced aside by an object that is either partially or wholly inside the liquid. And this is the fundamental principle known as Archimedes principle. The Archimedes principle states that the buoyant force is equal to the weight of the displaced water. And this applies to any kind of liquid, not just water. It applies also to gases. It applies to all kinds of fluids. Fluids means the fluid is a substance that can flow. It can be a gas or a liquid. This is Archimedes principle. I show an upward buoyant force acting upon this mass by blue color, and this upward force I denoted by Fb, and the downward pull of gravity as shown here, it is shown by red arrow. We see that the red arrow is longer than the blue arrow. It means that the force of gravity or the weight of an object is greater than the upward buoyant force when it is fully immersed inside the liquid. So only a part of the downward pull of gravity will be cancelled and the object will still experience downward force. In that case, the object is bound to sink to the bottom if the string holding the mass is cut off. So now I write the Archimedes principle. According to Archimedes principle, the magnitude of the upward buoyant force is equal to the weight of the liquid that have been displaced by an object. This is Archimedes principle. The weight of this water we denote it by WL. In this figure, I have shown a container containing the liquid, and this is the liquid level. And this is an object which is partially inside the liquid. Only the lower portion of the object is inside the liquid and the remaining portion is outside. The amount of water that this object have displaced in order to make space for itself inside the liquid, that amount of water corresponds to the volume of the portion of an object inside the liquid. I show that portion of the liquid which is displaced aside by by shading it. The water that was originally present in this region have been displaced aside. And we know, according to Archimedes' principle, that an upward force will act upon this object. An upward force is equal to the weight of water or a liquid that an object has displaced. So the buoyant force, the upward buoyant force, I show it by an arrow, and the upward buoyant force is equal to the weight of the liquid that is displaced. Now we further immerse this object into the liquid. It will displace more amount of liquid aside, and hence the buoyant force acting upon an object will increase, because buoyant force is equal to the weight of the liquid that is displaced. Greater the amount of liquid displaced, greater will be its weight and greater will be the buoyant force. So we note down the buoyant force increases as more and more of the object is immersed inside the liquid. And when this object is fully immersed inside the liquid, as shown here in the diagram where we see an object is fully inside the liquid, so it has already displaced the maximum amount of liquid that it can. It cannot displace more liquid than the volume of itself. Object cannot displace more liquid than the volume of itself. So maximum amount of liquid have been already displaced by an object. So in this case, when the object is fully immersed inside the liquid, the upward buoyant force acting upon an object will be maximum. It will not further grow the more you dip the object inside the water. Once the object is fully inside the water or inside the liquid, the buoyant force acting upon an object will be at its maximum value. It will no longer increase any further, even though you dip the object further into the liquid. Because if you dip the object further into the liquid when it is already fully inside the liquid, it will no longer displace more water. It will displace only as much water as uh, equal to the volume of the object itself. So the buoyant force increases, the buoyant force acting upon an object keep increasing as long as a part of an object remain outside the liquid. But once it is fully inside the liquid, however deep you take the object inside the liquid, the buoyant force acting upon an object will not increase further, because buoyant force acting upon an object will be equal to the weight of liquid that it displaces, and it has already displaced the liquid equal to the volume of itself. So we note down this, that when an object once fully inside the liquid, the buoyant force will be at its maximum, and no increase in the buoyant force takes place as the object is dipped further and further into the liquid once it is fully inside the liquid. The upward buoyant force increases as more and more of an object is immersed into the liquid. But when the object is fully inside the liquid, the upward buoyant force remains constant. Once fully inside the liquid, the upward buoyant force acting upon an object, if it is less than the downward pull of gravity, then downward pull of gravity will overcome the upward buoyant force and the object will experience net downward force and it will sink to the bottom. However, if the buoyant force completely balances the downward pull of gravity at a certain stage of the object being deep inside the liquid, then on balancing, the object will float on water surface. For an object to float on water surface, the buoyant force has to completely cancel or balance the downward pull of gravity. Once this happens, the object will float. But however deep you immerse the object inside the liquid, the buoyant force remains less and the downward pull of gravity is greater. Then there will be net force in the downward direction and object is bound to sink down to the bottom. So the condition for the floating of an object is that the buoyant force must not be less than the downward pull of gravity. If the buoyant force remains less than the downward pull of gravity, there will be a net force in the downward direction and object will sink. So we write the condition for floating. The object will not float, will not float when the buoyant force is less than the weight of an object. And the objects float when the downward pull of gravity, which is the weight of an object, is completely balanced by upward buoyant force. This is the condition for the floating of an object. Now, while you dip an object inside the liquid, it may happen that when only a part of an object is inside the liquid, the upward buoyant force becomes equal to the downward pull of gravity. So when the upward buoyant force becomes equal to the downward force of gravity, the balancing of forces will take place. The net force acting upon the object will be zero and the object will start floating with that much portion of it inside the liquid. So it is not necessary for the upward force acting upon an object to build as strong as the downward pull of gravity that the object must be fully deep inside the liquid. It is not necessary that object must be fully deep inside the liquid. A part of an object may be inside the liquid and it may have displaced enough water that the buoyant force, the upward buoyant force has grown and it become equal to the downward force of gravity. Once the buoyant force becomes is equal to the downward pull of gravity, there will be a balancing between the two forces and object will start floating. Let's do some more analysis of the case when object will not float. We have seen that the object does not float when the buoyant force remains less than the weight of the object, even when an object is fully immersed inside the liquid. So we know that downward force of the upward buoyant force is equal to the weight of the liquid that it displaces, and the weight of the liquid can be written as mass of the liquid that is displaced times the acceleration due to gravity. This is the weight of the liquid displaced, mass of the liquid displaced times gravity. We continue to write this inequality sign, and the weight of the object is equal to mass of an object times the acceleration due to gravity. G cancels from both sides and we have a condition in terms of the mass of the liquid that is displaced and the mass of an object uh, for the case of no floating. So when mass of the liquid displaced is less than the mass of the object will not float. Further, we can put this condition in terms of the density of liquid and density of mass. We know that the density, which we will denote by rho, is equal to mass upon volume or the mass per unit volume. This means that the mass is equal to the density times volume. Now mass of the liquid. We can write mass of liquid as density of liquid into the volume of liquid displaced. And then the mass of object may similarly be written as density of an object into the volume of object that is inside the liquid. In fact, the object is fully inside the liquid, and yet the upward buoyant force acting upon it has not built as strong as the force of gravity, and therefore it is sinking to the bottom and not floating. Now, when the object is fully inside the liquid, the volume of liquid that is displaced and the volume of object will be equal when the object is fully deep inside the liquid. We can imagine this block being pulled further into the liquid. So when the object is fully inside the liquid, it is easy to see that the volume of the liquid that is displaced will be equal to the volume of object itself. So we have volume of liquid equal to volume of object, and this volume can be represented by a symbol V. And now we rewrite this condition here as rho L times V less than rho O times V. Now V cancels out from both the sides, and we have rho L, that is the density of liquid less than density of an object. So this is the condition in terms of the density of liquid and density of object, under which the object will not float. So for an object to float, the density of object must be greater than density of object must be less than density of liquid. This is the condition for an object when it doesn't flow. When it doesn't float, the density of liquid is less than density of object. And for an object to float, we must have density of liquid greater than the density of object. So you only have to verify whether the density of object is less than the density of liquid. When the density of object is less than the density of liquid, it will float. For example, density of thermocol is less than the density of water, so thermocol floats. Now let us address the question of why does the ship float. We can understand this question with a simple example. Suppose a small piece of an iron, or consider this diagram. Suppose this is a piece of iron, and we know that the iron never floats on water surface, so it will sink to the bottom. But if the same piece of iron, is molded into a bowl shape, the same piece of iron molded into a bowl shape, I mean the same mass of iron is taken. Here the iron is in the form of a block, and the same mass of iron, if molded into a bowl shape, and when this bowl is placed on water surface, because of the shape, it will displace a large amount of water aside, and the large amount of water is displaced means the weight of that water will also be large, and we know that the upward buoyant force is equal to the weight of water displaced. So more the water displaced, more will be the upward buoyant force acting upon bowl shaped iron, and more the buoyant force acting upon the bowl shape iron means there is a possibility that the iron taken in the form of bowl shape will float. If the amount of water displaced is sufficient enough that the upward buoyant force acting upon the bowl completely balances the downward pull of gravity, then iron in the form of bowl shape will float. That is the principle involved in the making of ship. The shape, the shape of the ships are so designed that they will displace aside enough amount of water so that the upward buoyant force acting upon the ship will completely balance the downward pull of gravity without sink having to be, without ship having to be completely immersed inside the liquid. A large part, even if a little part of the bottom of the ship is inside the water displace will be sufficient so that its weight will be equal to the weight of the ship. The weight of water displaced by the liquid, if it is equal to the weight of the ship, according to buoyant principle, the weight of water displaced is also equal to upward buoyant force. So when weight of displaced water is equal to weight of ship, it means the upward buoyant force is also equal to weight of ship. I write here the weight of water displaced by a ship is equal to weight of a ship. And according to Archimedes principle, the weight of water displaced is also equal to upward buoyant force. So what we see that the upward buoyant force is equal to the weight of ship. The weight of ship is the downward pull of gravity, while the buoyant force is acting in the upward direction, and the two forces balance and ship will float. This is how an Archimedes principle have a simple explanation of why ships float. Thank you.